Okay, it should be good, maybe.
Okay, let's get started. Hello, all. Welcome and welcome to our next session of the Data Driven Learning and Control Seminar series. And this is your host, Nishan, and I'm honored to introduce today's speaker, Dr. Stefano Di Cairano. And his talk today is going to be about decision making for automated driving from control to optimization to data driven methods. And Dr. Cairano is currently with Mitsubishi Electric Research Labs, and he received his master's and PhD from the University of Siena, Italy. And then he went on to work with Ford on powertrain control. And in 2011, he joined the Mitsubishi Electric Research Labs. And currently, he's a deputy director and a distinguished research scientist at MER. And his research focuses on optimization-based control and decision-making strategies for automotive, factory automation, transportation systems, and also aerospace. And to be more specific, his research interests include model predictive control, constraint control, path planning, hybrid systems, and optimizations. And he has authored, co-authored, and contributed to more than 250 peer-reviewed journals, and is also an inventor in 80 patents. And Dr. Cairano was chair of the IEEE CSS Technical Committee on Automotive Control, and he's also contributed a lot to the Technical Committee on Optimal Control as a vice chair, and currently he's the inaugural chair of the Technical Conferences Editorial. And without further ado, I'll pass on the mic to Dr.
Thank you for the introduction and the invitation to speak. Again, this talk it's about decision making for automated driving, and I should say that as a training, I'm not a data-driven person. I focused a lot actually on physics and model-based design, but given that also I'm a practical person and we are developing technologies for the real world, I mean, data-driven methods in some way or others are always used, whether it's through system identification, adaptation, and so on. And with recent advances in machine learning and artificial intelligence in general, obviously these finds more and more use, even if you start from model-based design. So what I'm going to show is like certain problems in decision making for automated driving, how we can start from handling them with control approaches and then use also optimization, and eventually how we can use some of the data-driven methods to further improve or simplify the control architectures. So usually just I try to spend like 20 seconds, well, maybe 2 minutes, discussing a little bit where I come from, just because there might be some confusion. Again, I work for Mitsubishi Electric Research Lab. That's the North American research lab of Mitsubishi Electric Corporation. One thing that sometimes people confuse is that Mitsubishi companies, there are many, but they're all separated. So we are not Mitsubishi Motors. We don't make cars. We make everything that is electrical, electronics, electromechanical. And basically, we have some macro business area, industry and mobility, obviously, factory automation, robots, and mobility system from cars to trains to, cars, the car electronic, the onboard electronic for car, like as a tier 1 suppliers, and then trains, similar situation, and traffic control systems and so on. And there is an infrastructure business that does, again, a little bit, another part of the mobility, more the infrastructure for mobility, and then communication, satellite systems, and so on. And then so-called living environment, where that includes appliances and air conditioning system and building system, elevator, escalator, other monitoring situations. So obviously, the organization that's pretty big has a lot of business unit, and there are a number of, there is a fairly sizable research organization that supports it. The bulk obviously is in Japan with, I would say, conventional R&D labs in the Tokyo area and in the Osaka area. But then they also have some research labs abroad, one in Europe, split between UK and France, something in China, and then us in the US. And really our goal in the US is to look for fundamental research that can affect multiple of these businesses or very futuristic application. Again, automated driving being one, or at least definitely being one when we started more than 10 years ago. So we are organized again, because of this, we're really organized around not products, but fundamental area with things like control, optimization, machine learning, signal processing, and so on. And we work a lot with university. We host a number of interns, I think about 100 every year. We are 57 researchers, so there is basically 1.5 between researchers and interns. We collaborate with academia in different way. One good thing is that we publish everything we do. So there is a lot of papers coming out, and students come here to have internship with us. Usually at the end, there is a paper that's being written, maybe also journal paper if, some interns come a couple of times. Some people do part of their work, that take part of the work that they do here into their PhD thesis or master thesis and so on. Yeah. Okay, so now let's get into these problems that I want to discuss a little bit about. So again, I think that if you look about technology items, cars are definitely one of the most pervasive technology, maybe second only to computers. And there is close to 100 million new cars every year in the world, and there's probably about 1.5 billion in use, and that was 2016, so maybe that number has grown up a lot. So if we make a technology that affects cars, obviously we are making a large impact on the world, right? And there's probably no technology that is more relevant for cars that actually make the cars drive themselves. And I think for several years we thought, hey, this is going to come next year. And in fact, there were very bold statements that pretty much every year that says, oh, next year we're going to have autonomous cars on the road and so on. I think there are different perspectives about it. In my opinion, we are not there yet. And in fact, like it happens a lot of times with technologies. If you live in the industry side of technology, you kind of get used to it, whether you like it or not. There is a hype phase, and then there is a little bit of retraction phase, and so on. In particular, I think in the last couple of years, there's been a little bit of a contraction, but still there is a lot of investigation going on. We know that it's a technology that eventually is going to come and is going to affect a lot how things are happening. Why we have this pulling back? Obviously, there's been a lot of investigation of automated driving in very benign scenarios. The first time I worked on it was 2006, was in the Urban Challenge. That is supposed to be urban, but it was still in a desert in California, very nice weather. It was a mock city. Sure, there was some interaction between vehicles, but it's relatively benign to what I have like down my window right now, in the middle of Boston. And it's like a total chaos right now with a lot of cars going on all over the place, constructions. You might hear even a sort of pneumatic camera at some point and stuff like that. So real cities, real driving is much more complicated. There is a lot of interaction with other vehicles. There is a lot of unexpected events. There is a very bad weather. So there is usually some challenges that remain. Some of these are the robustness, the complexity, and their interaction with other actors on the road. But that's why we need to keep doing research, and the research in fields as diverse as control, optimization, and machine learning can certainly help. Not touching here on the perception, but obviously that's really important as well. Okay, so this is what I want to quickly talk about. And there is basically a big, first a big stream and then a few other snapshots. I want to talk primarily about decision-making and planning for autonomous vehicles. And I'm going to show you 3 steps. I'm going to show, and these are a little bit like the history that we had in the lab. So how we tackle the problems using primarily control-oriented methods, in particular set-based dynamics, to ensure certain safety properties. Then I'm going to switch and show you how certain things can be done with optimization solver. We know they can be done, but the big development here is that we actually develop specialized solvers that actually we can run in the vehicles in embedded controllers. And finally, I'm going to show you what we can gain by using learning. After that, I'm going to have some couple of snapshots more for the fun of it, related to some extensions and other application, and a couple of recent news about that. Okay, so for automated driving, when we are trying to do motion planning for automated driving, and this is basically the route that I take from my home to my lab, even that is not a very long trip. It's only about 23 minutes. I think that was during the pandemic. Right now it's more like 30, 35. But when you factor that in, you cannot really plan the entire motion at the beginning to the end. The computation is too large, still 23 minutes of path is pretty long at the rate of computation in a car. And the environment is going to change in the meantime. So there is really no point to do like the exact motion planning as a sequence of positions. Sometimes even if we look at the busy road, even the next waypoint, like the planning up to the next intersection might be too far in a single shot. So really what we need to do is to separate this problem into multiple layers. There's going to be a strategic layer, a strategic planner that's pretty much like the sequence of waypoint to travel from departure to arrival. That's what the car navigation system usually does for you. Then there is a tactical plan that are the physical driving action or sub-goals to achieve the next strategic waypoint. So if I'm here and I have to, my next waypoint is going to be the stop line over here, I'm going to do a lane change, a lane keep, and then a lane change, and then a stop to stop lines. And that's my next waypoint. And finally, there is a motion plan that actually, given this sequence of action, generates the trajectory for that action. There is also an additional layers, the control that actually execute those. So this is usually the architecture that we look at. I skipped the car navigation part because it's fairly standard, but obviously we have some sensing on the side. I'm not touching that at this talk, at least. But then we have our decision-making layer. That's my tactical plan, what actions they need to execute. There is a path planning. How do I achieve those actions? What's the motion that's going to achieve them? And then there is a vehicle control that actually executes. And here I just quickly list, in my opinion, when these layers are really needed. If I'm thinking about with respect to the autonomy level. So autonomy level 1 and 2, which is like the single function, the coordination of function, pretty much what's more or less on the road today, you really just need a good vehicle control. And if you do level 2 plus, the Tesla autopilot, I don't really like to call it like that, but some of the systems similar to that, GM Super Cruise and so on, you might need some levels of motion planning. But really, when you start to move to level 3, so extensive use in multiple conditions, and then level 4 full autonomy in closed area, and level 5 full autonomy everywhere, that's when you start to need also these higher level and more capable blocks. Now, I know that there is a lot of discussion going on in the community whether we do like end-to-end learning versus layered architecture. The reason because I like layered architecture is that they're flexible, meaning I can swap in and out blocks easily. They're customizable, so I'm in a company. Like eventually, if I build this system, I need to sell it to somebody, and somebody maybe just want parts of the layers. Maybe they have their low-level control done, and they want the upper layer. Maybe they have the high-level control done. So if I build it in this way, I can provide different blocks to different customers. It's also easier to validate and maintain. Like I can build it layer by layer. And if something fails, I can pinpoint what layer is having problems and try to fix only that without needing to, strip everything apart. So that's why we chose this. But obviously, there is a lot of discussion is how do we structure it and so on. And we're going to get back to that later. So when we look at least at the two top two layer, that's going to be pretty much what we talk about today. We're trying to determine a goal for the motion planner and then the corresponding motion plan. So really, you're looking at a system where you have some discrete action, like, change lane, stay in lane, cross an intersection, stop at the stop line, and stuff like that. So you have these discrete goals. You have some sort of interface, and then you're interfacing the goal with like specifications that you need to achieve with the motion, and that's going to be like a continuous problem. So overall, you have discrete components, you have continuous component. That's a hybrid system. Can we compute the trajectories for this hybrid system like in a general setup? Yes, we can. From a theoretical perspective, there are tools. The only problem is that they are very computationally heavy in the general case. So just solving these as a single shot, it's still extremely challenging, especially when you're considering hardwares that you can run in vehicles today. So really, the idea is to take the modular approach, and that basically separates that. So instead of having plus, we have arrows. So first, I'm going to solve the decision-making problem. Then I know what my interface is. And from the decision-making problem, I implement the specification for the motion plan. How do I do that? Well, the brute force approach is just I'm going to take every single discrete state and compute the trajectory to see if I can achieve it or not. Again, not very efficient because we're going to try to compute trajectories for a lot of unfeasible goals, which will result in a lot of wasted computations. The other one, that's what was done actually a lot during at least the urban challenge, grand challenge period, and I suspect with a lot of initial system, is I'm going to define some conditions for which I'm going to transition from one discrete goal to another discrete goal, and I'm just going to compute those trajectories. Now, having worked on that part, I can tell you that designing this transition when the graph, where the number of goals, it's complicated, it's really, really painful. We had to do automated driving projects for Japan, and there, as you know, Japan is very dense. The roads are also very dense, and there are a lot of complicated rules, and this automaton had at least 15, 16 states. Like transition between these 15 or 16 states, it was really, really painful. And that's even without accounting a number of additional states for, fault management and so on. So what can we do instead? We can just determine if the transition from one mode to another mode is feasible, determine it before, just looking at the conditions and the graph, and then only generate the trajectory for those transitions that are feasible. Now, this automaton does not need anymore to be non-deterministic, meaning you can have intersecting sets, so you don't try to generate these rules to be unique, which makes it extremely simple. Actually, you don't really need to design any rules because your feasibility checks will tell you whether you can transition to a state to another. And then the result is basically that you're going to have a non-deterministic finite state machine with guaranteed feasibility, where at some point you're going to solve the motion planner will resolve the non-determinism. Now, these all designs are based on a number of control concepts, in particular set-based dynamics, where we take a set and we look from that set what are the set of states that I can reach at the next step, or from which states I can get to that current set. So the preset and post set. Not going to spend too much time talking into it because it's obviously it requires a lot of discussion more than we have today. But my point is that what you're trying to do is to use this set-based dynamics to guarantee that once we're gonna compute the trajectory for a state or for an action, that trajectory will be feasible. Okay, and how do we do that? We're basically going to use, in this case, some models. We have a course model for the decision maker, a planning model, fine, for the motion planner. Obviously, the decision maker needs to run quickly, and so it's very approximated. The model is very coarse. The motion planner has to be much more precise, so it's going to have a higher precision model. we need some reconcile because we're going to make a decision on one model and try to apply the other. So we need to have some condition that let me say, hey, if I can compute a trajectory according to the coarse model, I know that there is going to be a trajectory in some neighborhood of it from the fine model. So if I can compute a trajectory according to the approximated model in the decision maker in the top level, I know that the motion planner will be able to do it to generate a trajectory in a tube around, and that's where the sets come into place. Okay, so what we do is that we consider both the liveness of the system. So if I'm taking an action, I need to be able to achieve the goal of that action. So what I do is that I have a goal set, for instance, this blue square for stopping at the stop line. I'm gonna compute the set of states from which I can reach that goal. And I'm gonna enable that goal only if the current state of the vehicle is inside one of those sets, which means that I can get there. So if I'm too close to the stop line, I'm not gonna allow this lane change, because in order to complete the lane change, I need to break the stop line. And the other set is like the safety. Safety means that usually I don't want to be in collision, or I don't want to go in areas where I shouldn't be going, more in general. So what we do there is we compute the sets from every of these no-go region. We compute the set of states from which I necessarily go into that region, and we stay out of it. We stay in the complement. Because if I try to go in the set, there is no maneuver that allows me to avoid entering one of these bad areas. So we just, so here, from this point, red point, no matter what you do with your input, whether it's the maximum or the minimum, we are always going into this bad set B. So we definitely cannot stay, we do not let the vehicle enter this green area. Okay, so then we get safety and liveness. And then once we get these, basically you can simply determine what are these macro states for which the goal is into the live area and allows me to stay in the safe area, and just by doing a number of checks, and we provide all these goals to the motion planner. And at that point, the motion planner just compute trajectory for this. You can do it sequentially if you like. So you start with the more likely mode at the beginning, or you can do it with any form. We use a statistical method that's pretty much like using a particle filter for motion planning. And that gives us basically trajectories that are guaranteed to converge and to achieve the corresponding goal. So this pretty much how it works in a simple test bench. We have a number of these mini vehicles. The red one is the autonomous one. The other two are still autonomous, but fairly dumb, so they just follow their line and stop at the intersection for 3 seconds. You can see trajectories that are generated in purple, and the green one is the chosen one. And here you have the automaton, with the red are the modes that are possible, and the green is the chosen one. So when we run these, and hopefully it does, okay, so the video comes decent, but you see that there is at some point you have only one feasible mode. You're crossing the intersection, now you have two, you decide between lane change and lane keeping, depending on where you are. And when you get close to the stop line, now you cannot lane change anymore. So you have to just keep following. Here you can either lane change or stay behind the vehicle, or stay in your lane and pass it. So obviously it's more reasonable to pass and then change lane later. Here you're gonna change lane and stay there until you get to the intersection, and so on and so forth. So this is basically like the application. This continue, but I think we can stop it now. We did test it in real scenarios. This, I'll tell you that we have the test, but those obviously are a bit, sort of protected. This is actually real data from the test showing what the decision maker will take the reasonable choices, and we can run it for a very long time. So again, our colleagues in Japan did it. So unfortunately, the layout is a little bit different, but here you can see the decisions that it's taking, and now the automaton is much larger, so I really cannot plot it. Again, it's these 16-stage sections, but it basically say that you're basically in an intersection, and now we're doing lane keeping, and we could do lane change, and in fact, actually the driver does that, and so on. So this is actually another airport in Japan. There was a project to run their autonomous vehicle during the Olympics, except as you might remember, the Olympics were really happening when they were scheduled to because of the pandemic. So unfortunately, we didn't. The demo happened, but not during the Olympics, so it was a little bit sad, but still successful. So that's control. And again, a lot of the questions that I get is usually, why do you get 3 layers? Can you do with a different number of layers? And my answer is usually, sure. 3 layers is what I'm comfortable with, but actually you can do with something else. If we have smarter layers, we can actually do with 2. Where we do some decision-making and an approximate planning at the top level, and then we use a slightly smarter predictive control that also has a lot of collision avoidance at the lower level to refine that approximate motion plan. Now, the thing is that this problem, now we really need to solve some sort of mixed integer problem, hybrid system problem. The approximation allows us to go to from a hybrid system with nonlinear dynamics to a hybrid system with a piecewise linear dynamics. And then at the lower level, we can solve a nonlinear optimal control problem to refine it. So is this feasible for onboard ECUs? I mean, a lot of people use mixed integer optimization, and they know that, yeah, sure, we can run it with Gurobi, maybe even really fast, but Gurobi, you can't compile it in a car ECU. I've asked a few people if they tried. I haven't seen yet a paper where they said, hey, yeah, we run Gurobi in an ECU, like this space and so on. Okay, so for implementing this for real, we need customized solvers. The NLP can be converted into a sequential quadratic programming framework where there is a very special structure that can be used to speed up the computation a lot. And in fact, we spent a lot of years between 2010 and 2015, 17, developing these solvers. Some of them actually are in production as of today, but you can use active set methods, you can use interior point methods, and those, they're very good implementation that you can run in embedded ECUs, as I just mentioned. The frontier, when we started this work, was mixed integer programs. Again, I haven't seen any that works sufficiently well in embedded platform. So you know that basically mixed integer programs, the standard approach is to use a branch and bound methods where you represent your problem as a tree, where every branch fix one integer variable to a certain value. And so you start from a root node where all the variables are relaxed to be continuous. You decide you compute a solution for that. That's going to be a lower bound to your optimal cost. Then you choose one variable, you fix it on one side to 0, on the other side to 1, and you come with 2 different problems. You choose which one to solve, and you get, again, a different lower bound, still a lower bound that should be not as good as the previous one. Then you fix another variable until you get an integer solution. That becomes your upper bound because it's one feasible integer solution. And you can keep doing, but now that you have a lower bound and an upper bound, you can decide which branch you're going to cut until you actually complete your tree. Now, for solving these...
Dr. Cairano, sorry.
Yes.
So there's a question, if you don't mind.
Sure.
So question is, what are the computational implications of using mixed integer?
Well, so the computation implication is this one. Mixed integers tends to, it's a known polynomial algorithm. So right now it's class of NP-hard. So in order to actually solve this tree, you have to solve a large number of optimization problems, which means that you need a lot of computations. if you just try to solve all the problem. Now, usually mixed integer, what I'm going to tell you is that there are some heuristics that allow you to speed up the computation a lot so that you can fix them. You can set a certain number of computation in a fixed amount of time. Again, we need to solve a lot of problems. So the first approach is to actually have a very good solver. And in particular, as I mentioned, you're computing lower bound and upper bound. So if you have a solver that can immediately tell you whether it's above or above the upper bound, then you know that you can stop the solution. So we did some work in that domain using interior point methods. And then there is a lot of decisions that you have to make in how do you select the node that you're gonna investigate. And again, since you want to quickly get to an integer feasible solution, you want to go depth first rather than breadth first, because again, you want to get to the bottom of the tree as soon as possible. Then you have to choose which variable to branch. I'm gonna choose UI or UK. And there are some techniques to do that. Some of them are very heavy, but we can get approximated techniques that still tell us a lot of information, but they're much cheaper to execute. And again, here, cheap computation is everything. There is a lot of variables that you can remove because, for instance, think about if you have some variables, integer variable associated to eating or not eating this obstacle. If you start from here in the first 3 steps, for sure you're not going to hit the obstacle. This is, if you compute the reachable set, again, the set of potential next states, you know that there is no intersection. So if you do this analysis quickly, and there are ways to do it, you can eliminate a number of variables because you know that the solution will never be able to hit the obstacle in the first 3 steps. And that's very similar to the reachability techniques I mentioned before. And then you can do a bunch of things related to worm starting. And if you put all these pieces together, the fast solvers or this heuristic and so on, you can get to a point where you can actually solve these mixed integer problems fairly quickly enough that you can use it in vehicle decision making, where you want decision rates of maybe 2 to let's say 0.5 to 4 Hertz or something like that. So these are all cases where we do it in simulation first. You have an obstacle that you have to avoid. Okay, it's relatively simple. There are integer variables with the obstacle avoidance and the stop enforcement. Okay, and you can see the computation at the bottom. Here we are in the order of like 20 milliseconds. And this is running a mixed integer solver. Here, a situation where you have multiple obstacles. Some lanes, the white ones are closed, so you cannot go there. So there are exclusion zone, collision avoidance zone. There are also timing constraints between how quickly you can make lane changes, because if you drive, you don't like to do like bang bang. So we impose some timing constraints. If you have done a lane change, you cannot do another lane change for the next 3 seconds, things like that. Okay, and again, these are all related cases. I show. I might stop now, but it shows on a straight road, but they work on relative coordinates. So basically, we do curved road as well. Again, for the sake of time, these are experiments where we run the same vehicles as before, but you can see the decision-making here. And what happens is that there needs to be, since the decision-making is approximating the obstacle and approximating the motion of the vehicle to be linear, we need to have a lower level that's a little bit smarter. So here we have our customized linear MPC based on sequential quadratic programming with our own solvers. And the main difference is that the upper level uses boxes for obstacle avoidance. The lower level, since now we're solving a nonlinear problem, we want it smooth, it's using ellipsoids. And obviously the high level, it's a coarse model with a fairly large sampling period in the order of a second. The low level is if I remember correctly, 40 Hertz, so 25 milliseconds update rates to be able to ensure constraint satisfaction continuously.
Dr. Cairano, there's another question.
Sure.
Yeah. So The question is, branch and bound may only work for mixed integer QPs. Where,
Actually,
like, how is it? Sorry.
Okay, so please continue. So
sorry, I'm reading the question. Yeah.
Sure. I thought it was finished. Sorry.
Yeah. Works for mixed integer QP where the subproblems are QPs. And how about mixed integer nonlinear problems where the subproblems are NLPs?
Yes. So technically, branch and bound works for every method. In fact, we are running my program for the afternoon. My program for the afternoon is actually review a paper with a student that we work on mixed integer nonlinear. The problem with the nonlinear part is that you're only gonna get a local solution. So it's unclear whether you get a good local solution. But we had a paper at CDC a couple of years ago, maybe a few years ago, like 3 or 4 years ago, on mixed integer nonlinear, using this method but extended to mixed integer nonlinear. The approach we like to take here is to use an approximated solver to solve a global problem and then refine the nonlinear dynamic local. Okay, but I suggest you might want to look at my page on Merle. There's going to be a CDC paper, maybe 2022 or 2021, on mixed integer nonlinear programs with application to vehicle control. And we can talk more offline or later at the end of the talk if you like. I can show you a couple of things, how things are done. Okay. Okay. So that was obviously a test with mini vehicles, so not very clear whether it actually works in real cars, but these are computational tests of the same scenarios that I show in the simulation run in the DSpace MicroAutobox 3 and Scalexio. So these are good representation of what the computational power you have in today's car. Maybe not today, maybe next generation, but let's say 3 years ahead. And you can see that computation time is in the order of less than 200 milliseconds, less than 800 milliseconds for the two cases, with memory occupancy in the order of 16 to 18 megabytes. Just to give you an idea, if you look Gurobi, the library is much bigger than that, so large that you cannot even load it in the memory. Okay, so actually we can fit technically in cars. But the question we still got from some of our collaborators is, can we get an even cheaper implementation of it? Can I get something that has the same performance, but the implementation is much simpler and require even less computational power? And that's when machine learning comes into place. So if you think about it, from what I showed you before, if the integer or binary variables in an MIQP are fixed, then the optimal solution is obtained by computing a QP. This method that I show is basically like a hybrid MPC. So we know that MPC is a static controller, which means that if I fix an initial state, for that, whenever I see that initial states, the optimal decision will always be the same. Which means that given the initial state, I can try to learn, given initial states, the entire solution. Now, the entire solution is going to be high dimensional, so it might be tricky, but I can try at least to learn some part of it, the parts that are more relevant to me, more critical to me. In particular, I can try to learn the integer. So, and this is aligned with certain techniques that are going on right now in the optimization community, where people are investigating how you solve combinatorial problems via machine learning. Okay, combinatorial optimization problems via machine learning. So we came up with a number of methods. First one was a few years back. It's called Prism. It's basically a recurrent neural network that does where we do pre-solve and learning of the integer variables. So again, it's a set of RNNs that basically provide us the integer variables. And after we get the integer variables, then we can compute the solution via QP. More recent methods that actually we specialize for autonomous vehicle is using deep learning and equivariant architectures. So just, again, I don't know if they are well known or not, honestly, but equivariant architectures are architecture where if you change the order of the inputs, you basically change the order of the outputs. So they're basically permutation equivariant, while permutation invariant are the ones that if you change the order of the input, the output remains the same. We use an architecture that uses both these components before the recurrent network. In particular, here we use LSTMs. And the idea is that you don't want to train for obstacle 1 being at one location, obstacle 2 being at another location, and the opposite. You want that if you reverse the order of the obstacle, the output is going to be just simply reversed. So by using these equivariant networks and that are implemented as networks called equivariant deep sets, we allow to basically remove all the combinatorial part related to inverting the order of the obstacles, which reduces the amount of data we need for training. And with that, we get in a certain number of vehicle tests, obviously this one in simulations, we get these results. So these are the infeasibility rates for different number of obstacles and different length of horizon. And you see that obviously we improve from feed-forward network only to LSTM, which would be the LSTM implementation of the RNN that I showed in the previous slides, to this equivariant deep set without recursive network to the recursive set. But still, we have some infeasibility. And that's because our network gets wrong. Okay, so the next step is we don't use a network, we use an ensemble of networks. Fine, that makes sense. In fact, here you see that we have an ensembles, especially for the equivariant parts. But still is going to remove it. But the point is that with machine learning, we can never be 100% sure that we're not going to take the wrong decision. So what we do is that we go back to embedding some optimization part into it, where now we have our mixed integer problem that we use for training. We train the neural network. The neural network provide guesses for different trajectories of the integer variables in the QP. We use them to solve now a soft constraint QP in order to ensure we have feasibility. We choose the optimal one, and then we project with an optimization problem into an actually feasible solution. Okay, so this last step serves as a safety mechanism where we get the previous trajectory, we use the previous trajectory as a reference trajectory, but now we enforce the constraints. Okay? And by doing this, we get 100% safety in a number of tests in Sumo. You can see here on the left side the closed loop cost, where obviously the MIQP is one, is the best one. But you see that using 10 neural networks with the safety mechanism, we are probably within less than 10% error. But when you look at the computation time, especially if we can run this 10 neural network in parallel, we are orders of magnitude faster, especially the worst case, which is what we need to design the embedded system for. It's a couple of order magnitude faster than running the QP, the mixed integer solver. Okay, so again, control, we get the safety from the control, the sets and so on. Optimization, we get obviously a very good solution, and we can reduce even the number of layers. Machine learning, we can actually simplify the computation and retain the same performance. So that's pretty much what I want to show and how we combine everything to achieve the solution for these problems. There are a number of applications that we have done of these beyond autonomous vehicle. There is something about coordinating multiple vehicle, both autonomous and non-autonomous in closed scenarios where we have control also on, for instance, the traffic lights. So we can use the traffic lights to control the non-autonomous vehicle, while this coordination center sends velocity target to the actual vehicle, similar to a control tower with aircrafts. And so you get some of these results here in Sumo, where on the left we have our methods, on the right we have some standard adaptive traffic control lights. Obviously, you need to stop some traffic, so there is no non-zero queues, but you can see that the queues on the left are much smaller than the queue on the right, just eyeballing them, right? And again, here it's a mixed traffic. The blue vehicles are the autonomous vehicle, the red vehicle are the manual vehicle. Trick is control the autonomous vehicle directly, control the manual vehicles indirectly to the traffic light. Now you have all these switching conditions and so on. That's where the mixed integer come into place, and you can further simplify with machine learning. And you can do it in a centralized way, but obviously the mixed integer problem becomes very heavy. You can decentralize it by adding some safety condition, and that's gonna give you something that you can actually solve. The safe machine learning work we actually we first applied to drones in a slightly different context. There, we wanted to investigate teams of drones. Now, if you try to, and our collaborators in Japan actually were interested in seeing what they can do with reinforcement learning. The point is that if you have a lot of drones, the reinforcement learning problem becomes really heavy to compute, and it might fail just due to local minima. So a solution that we found was actually to solve independent reinforcement learning problems, and then apply this safety mechanism at the end, in this case more based on the set-based method that I showed at the beginning of the presentation, to coordinate the motion when they come close to each other. And when you do that, you can actually see the drones, that each drone is basically ignoring the optimal trajectory of the other, but if they come close to each other, they kind of avoid each other in an optimal way. You can do that centralized with, again, like a control tower, but there is also an extension to have it decentralized. It allows to handle stochastic uncertainty. And you can see in the left that if you try to do reinforcement learning only, there are a number of situations, the orange one, where the drones come into collisions, if you start from there. While when you use this safety enforced RL, everything is green, meaning there are no collisions. As I'm getting to the end, I just want to show a couple of things that these things being happening in the real world. As I mentioned, we develop a lot of solvers, and some of these solvers ended up in a product a couple of years ago. Well, it has been on the road since 2022, where we actually solved the lower level problem that I showed you for the mixed integer part. So it's a nonlinear MPC that does basically all the ADAS level 2 and 2+. More recently, this is actually a very recent news, and maybe I'm able to show some of the video. I don't know if they play the yard track YouTube, but basically this is an application of a lot of autonomous driving technology to logistics, in particular these big shipping yards. So these trucks are all being controlled by autonomous guidance. And obviously these are much more complicated because you have the articulated component, and you have a situation where you have to
uses a robotic arm
achieve a connection between the tractors and the trailer that needs to be very precise maneuvers and so on. So this has been, we work on that for 2-3 years on a very, sort of quiet way, and it was just announced publicly a couple of months ago, if anything. So these are basically, what we can do using control, optimization, machine learning, some of the benefits we can get from each of them, some of the real world sort of applications and potential impact for them. There are still a lot of problems to be solved for automated driving. There is bringing perception into the picture. How does perception affect the control? We're looking at methods called perception-aware control. We have done a lot of the theory. Now we're working on the applications. There is fault tolerance. because sooner or later something is going to go wrong, and that's normal. The point is how you're going to handle the faults, and how do we make sure that in the faults nothing too bad happens. And that brings me basically to conclusion, where we say that sort of guidance and control for autonomous vehicle is still very challenging. I think maybe some of the hype has been toned down now, and we still realize that these are very difficult problems. It makes it better sometimes if you do this divide and conquer approach, where we construct different layers and we try to build a little bit also from top down, from bottom up, the solution. We can find definitely a good place for both control, for all the three of them, control, optimization, and machine learning, to achieve the overall solution. I usually like to use all the tools that I have in my toolbox, not just use only one. I think if you use multiple tools, you get usually to a better solution. There is still a lot of open research problems, especially with the perception integration and the fault tolerance. And also an important thing is that even if we feel that, sometimes autonomous driving, we keep saying they're there, but they are not there. But the research we do for them, it does help a lot of other fields, as I show you in the logistics side and in the drone, and some of the application of the drone actually can be applied also. And we did apply them also to air traffic control systems. So that brings me to the end of my talk. These are some of the works and collaborators for what I showed you today. Obviously, a lot of work is done in collaboration with colleagues and interns. And thank you for listening. And if there is more questions, I'm happy to answer.
Thank you, Dr. Cairano, for your talk. It was really interesting to see how you break down things and solve them and bring things up to the industry standards when it comes to difficult problems like autonomous driving. There are a few questions, and I'm just going to direct them to you. So,
yep.
The first question is, could you elaborate more on the technique to solve mixed integer QP problems without centralization?
Without
centralization?
Myself. So, I mean, mix it. So if we talk about so is it this one or for the drones?
I think it's from before.
So before actually was centralized, like here the mixed integer is centralized. What we actually do is that we try to guess the integer. We train a network to guess the integer part of the mixed integer problem. So that once the integer part has been guessed correctly, then what we remain to solve is just a QP. Okay, so it's just basically guessing some of the variables. And there are different ways to do it. Obviously, the trick is how do I maximize the right guesses? The smaller the it is, this equivalent network allows to basically reduce dimensionality, because you don't care anymore your permutation invariant. So even if you are high dimension, you are basically living in a manifold in this high dimension. So it allows us to do more guesses with fewer parameters. But still, we need to make sure that nothing goes wrong. So we need to correct the solution at the end. Make sure that we never violate the constraints. Otherwise, every constraint violation is a potential accident.
I think there is a follow-up question on that sense. Like, the question is, do you use any verification tools to ensure some safety properties based on reachability analysis, for example?
So that can be done. It's not in this work, it's actually on the drone work. So all the set-based methods that I show you at the beginning for control, these are all like verification techniques that we use also for design. So you can do it real-time verification. Usually we prefer to do design with guarantees, which is, sort of use the verification tool at the design time. But this one, for instance, for the drones, that's what it does. Here inside, there is basically a reachable set, and you ensure that you stay in the set where no collision occurs. So it's a sort of like safe set compute with reachability tools. In this one for vehicles, we didn't apply, although we could. It's just for this project, it seems more natural to use here an optimization-based method as opposed to a set-based method. But you can take out this feasibility projector and apply something like we have for the drones, which is a safety-based projection, like a reachable set-based projection.
Thank you. There is another question. I think it's related to the previous question about centralization. So it's more related to the traffic signal control problem, and there's viewing it as an mixed integer LP. And so curious about how to solve it in a decentralized way.
Yes, so correct. So basically what we do, so that was my initial guess. But basically you see here we have a network of intersection, right? Imagine that this network is pretty big. What you can try to do is to divide it into blocks. The smallest block is going to be like a single intersection. A full decentralized is just, you're going to solve an intersection each on its own. Now, that doesn't work really well because the traffic flow couples the intersections. So what we really do is that we solve for single intersection, but then we get desired flow rates from a centralized problem. So we build it hierarchically. At a high level, we solve a hierarchical problem that determines at every intersection in every direction, what's the average vehicle rates that they need to go through. And that becomes like a target for certain quantities in the intersection controller. Now, this problem at the high level can be built in two ways. One is a mixed integer program of much smaller dimension, and especially dimensions that are independent on the size of the network, because you're just looking for, on the number of vehicles in the network, but only on the number of intersection. Or you can even relax that and just solve an LP relaxation, because since you're solving a relaxed problem, an approximated problem anyway, you can also relax some of the other integer variables. And then this goes to the single intersection controllers. So now you have a single controller that controls the vehicle in an intersection, and that obviously the complexity of that depends on the number of vehicles, but only on that intersection. So you can bound it because you know approximately how many vehicles, worst case, you can have in an intersection. By combining these two things together, we get performance level that's going to be the dark green and the purple. You get to performances that are very, very close to the centralized one, that's the red, but you can see that the computation time is, again, an order of magnitude less, and especially it doesn't scale with the number of vehicles.
Thank you, Dr. Cairano. I have a question about using machine learning, basically.
Maybe?
So,
can you still hear me?
If I get it correct, can you hear me? Yeah, I can hear you. Yeah. So if I get it correctly, we are training some models, and once we've trained models, we can just use them on the vehicles directly. And what's the scalability when it comes to coordination with multiple various traffic stations?
So you were kind of breaking a little bit here, so I'm trying to interpolate between words. So that's for the learning part. Again, here there is not much learning. At least we did some learning version. It's not published yet, but it's basically learning the top level. When we go around here, yes, the model, we try to learn the model, and then we can use them on line, in the vehicle. The learning is done offline because we need to get the solution of these mixed integer programs that's done offline. And then once we basically have a guess, then we can download the models with the solver. And now it's just a smooth solver, just our standard QP solvers. into the vehicle. And now we have only the network and the standard QP solver, as opposed to having the mixed integer solver.
Thank you, Dr. Cairano. Yep. Thank you so much for your talk. And Andres wanted to pass his regards. Like he attended the talk on YouTube Live.
Yeah. Unfortunately, I don't know what's happening, but our connection seems to be going really bad right now. So you're kind of frozen on my screen. I hope you guys can see me still.
Yeah, I think I'm also getting a frozen screen. I think it's just bandwidth problem. Yeah. Thank you so much for giving us this talk. It was really insightful, and I thank the audience for also asking really good questions and helping up with the discussions. See you until next week, and have fun. Thank you, Dr. Cairano, again.
Thank you very much for letting me speak, and have a good rest of the day. Thank you. Bye.